Okay, so this one, I don't know if we want to do this one. I just want you to see, I think this is kind of where we left off, just sort of saying that we could do this one. All it's asking us to do is the derivative of a composition. And so if u is defined as this this function of x up here, this polynomial, and f is defined in terms of u as a quotient, then this is kind of a big ugly problem, isn't it?
Yeah.
We've got this 4x squared plus 3x plus 1, that quantity that on the top is times 4, on the bottom it's squared plus 5, right? So that's a big, that's a big ugly problem. But if all we're trying to do here is find the value of the derivative when x is 0, well, it's not as hard as it looks. Okay, how could we go, and we'll decide how much of this we actually want to do. We can do the whole thing if you want, or we can just kind of. Okay. Okay, so if we want to differentiate this in, if we want to differentiate the composition, so we're really just doing f prime, right? We're trying to come up with f prime of x here. F prime of x is really just f prime of u times u prime, isn't it? Right?
Yes.
F prime of x, another way of saying that is df dx, right? And that's equal to df du times du dx, right? If we write the chain rule out in that way, so it's written using the ratio forms of the derivatives, remember how we look at those, we can just kind of say, okay, algebraically, this works, doesn't it? Because the du's cancel. Okay, what does that look like in terms of, this other notation for derivatives? Well, it's just going to be f prime of u times u prime of x, or just u prime. Okay, so if we look at those two links in the chain then, what is f prime of u if this is f of u? How are we going to do that part of the derivative? What's the rule that applies there? Yeah, it's just quotient rule, isn't it? Yeah, quotient rule problem. So this equals, then the first link is going to be the quotient rule differentiating this function of u. Okay, so what's that give us?
2u.
U squared plus 5.
Okay, so we got bottom times derivative times 4. Okay. Minus 4u times Kendall?
2u.
2u. Good. There you go. Okay.
Got me?
All over.
U squared plus 5 squared.
Okay, good. So there's the first link in the chain, right?
Filthy.
Times u prime. Well, there's u prime, right? Yeah, so what is u prime? 8x plus 3. Did everybody see that?
Yes.
Okay.
Alright.
Kilo.
Okay.
Actually, it's
I'm impressed.
Yep. Okay, now this looks pretty bad, but what's nice about this, we've been bailed out by this problem because all they're asking us for, look at this, they just want to know the value when x equals 0. So that's really no big deal. If we want to find the value of the derivative when x equals 0, well, at 0, u just equals g of 0, doesn't it? What is it? 1. Right? So u, we can substitute, being as we're trying to just numerically evaluate this derivative, we're going to make a substitution there. All of the u's, we're just going to substitute 1, right? Because when x is 0, u is 1. Sounds like bad grammar again. And then over here, we're just going to plug in a 0 for x. And we got it, right? So it really ends up being not a very hard problem because we're trying to, they don't want this would be a little tougher. If they wanted us to write out this derivative function as a function of x, well, man, that's gonna be, then I gotta substitute all those u's and simplify, and there's a lot of algebra work to do there, but if we're just trying to get a numerical answer, substitute and simplify the numbers instead of the variables, right? So then we just get, what was it, 1 squared plus 5 is 6 times 4, right? 24 minus 4 times 1 is times 2 times 1 is over 1 squared plus 5 squared, right? Times 8 times 0 plus 3. That's our answer, right? Just simplify. So 3 over 36 reduces to 12. 24 minus 8 is what? 16 over 12 is what, 4/3?
Yeah. Let's go with that. Sure. Trust it.
I trust you.
Make sense?
Yes.
Okay, so you're a fan of these kinds of problems. When you see something like find the value for a specific value of x, those are good problems. Those are the kind that you're gonna be able to do the calculus and not have to simplify. Just plug in values and get a number. Okay, questions? Does that make sense? Okay. Okay, here's another one. Let me make this a little bigger.
It's big.
You were gonna say that?
No way.
Okay, yeah,
Get
these
that over
these I think are, this is one I want to take a look at. So we're trying to find the equation of the tangent line to the curve when t equals negative pi fourths. Now this is, by the way, what we call a system of parametric equations. Okay, and the reason we call it that is because we've got these two equations that are written in terms of the common parameter, t. Okay, this is normal. We see this a lot. Those who are in physics especially,
That's not me.
you physics types in here that are taking physics, you guys have done kinematics. Have you looked at like projectile motion yet? Okay, so that's probably where you're headed pretty soon, is projectile motion. This is, you're gonna see this kind of thing quite a bit with projectile motion. Now here's a great way to think about projectile motion that'll kind of just give you a little insight into why these parametric equations might be useful. If you launch a projectile, let's just ignore air resistance, okay, for now. If we launch a projectile, when it's in free fall, as soon as it leaves the barrel, if you know, whatever, it's a cannon or whatever it is, ignoring air resistance, how many forces are acting on the projectile? One, just gravity, right? In what direction does gravity act? Okay, towards the center of the earth. So we could say downward as defined by towards the center of the earth, right? So, okay, so if that's the case then, if you break up the motion of the projectile into two components, we'll call it a horizontal component that's moving, you know, in the x direction, that's parallel to the surface of the ground, and a vertical component that's acting, you know, the y direction, just acting, you know, up and down towards the center of the earth or radially away from the earth. Which of those two is affected by gravity? The one going up. What about the one going sideways? No, not at all, is it? So what's interesting about projectile motion then is that it's the component, it's the tangential component or the horizontal component of the motion is unaffected. There is no acceleration along that component because the force is acting perpendicular to that motion. Now, what's useful to do sometimes is to think about this in terms of perspective. So let's take, we're smack in the middle of football season, so let's take a football, how about it? And you can test this. If you ever, like, for sometimes the big bowl games or the NFL playoff games, a lot of times they'll show pictures from the blimp or they'll show pictures from up high looking kind of down on the field. I want you to put this to the test over Christmas vacation when you're watching the bowl games and whatnot. Mm-hmm. When they show a picture from above and you see it like a, you know, long pass, watch the football carefully. A lot of times they're slowed down, and you'll notice that the motion of the football, it just seems very uniform. And you really can kind of see this, especially if it's in slow motion. if we're looking at here's our long bomb that's being thrown. If you're looking at this, if you isolate this from two perspectives, if you're gonna look at it, here's the eyeball over here. Looking at this thing from this perspective, what do you notice about the football? From this perspective, it's only going up and down. It's only going up and down. In fact, if you look at it, it's going pretty fast at the beginning, pretty fast up from this perspective. But as it nears the top, it comes to rest, it slows down and comes to rest and comes back down, right? You're seeing this from this perspective, it's exactly the same thing as that, isn't it? Right?
Yep.
Because you've isolated the vertical component of the projectile motion. That's the accelerated component. Okay, it's the same thing from this perspective. It's just throwing the ball straight up. It's going fast, it slows down, reaches the apex, speeds up in the opposite direction, comes back to your hand. Now, what if you isolate this perspective up here? So here's the eyeball looking down. Whoops, here's the eyeball looking down, right? If we're looking down from above, what do you notice? Yeah, it's like a hockey puck sliding on frictionless surface, right? It's just moving along, steady, constant speed, doesn't speed up, doesn't slow down, right? Okay, so you can kind of get an idea that this parametric equation stuff could be pretty useful, right? Because we get two completely different kinds of behaviors. We get constant motion horizontally, and we get accelerated motion vertically, but they're totally separate, right? I'm not going to go into too much more detail than that right now, but that's one of the things that you're going to be doing in physics. That, you know, you're going to set it up like this, and you look at it from those two different perspectives. You're going to purposely separate those two, because this is a pretty easy one to deal with, isn't it? Right, this horizontal one, constant motion is, constant velocity motion is very simple. This is the part that's a little bit more complicated, but if you can isolate that acceleration, you can set up a pretty simple equation of motion there. I mean, really, you could say, if you want to know how far this ball is going to go downfield, you could just ask the question, well, if I just isolate the up and down part, how long does it take to go up and down? And in that amount of time, I can just figure out how far that ball has moved at constant speed horizontally, right? To answer the downfield range problem. So, you get the idea? Okay, so there's the setup. You'll deal with that more in physics. We'll look at this a little bit more. We're going to look at some examples of coming up in the next unit about how could we, find the angle that optimizes downfield range, that sort of thing. And we'll even look at some instances where, what if we consider air resistance? Well, what's that do to it? If we throw in an equation that does take into account air resistance, how do we change that angle in order to get that maximum downfield range? Okay. Get there soon, though. Not for now.
I understand that.
Okay, for now, here's our setup. Here's our parametric equation. We want to come up with the equation of this tangent line, and we're just looking at like this. Right, we've got this curve. We want to know when t is equal to negative pi-4, we're going to be someplace on this curve. What's the equation of the tangent line? Okay, well, what are the two components we need to come up with the equation of that line? What are the two pieces that tell us? Okay, well now, we don't need any fancy physics stuff for now. We're just thinking this is purely just math. If I want to come up with the equation of a tangent line, what are the two ingredients for the equation of any line? Okay, I need a slope and hopefully the y-intercept, but I just need a point, right? If I had a point and a slope, we're set, okay? So what about the point? Let's do the easy one first, the non-calculus part. How can I come up with the x and y coordinates of a point? Okay, good. I'll plug in negative pi over 4 for t into each of these two parametric equations, because what these are doing is they're giving me the x component as a function of t and the y component as a function of t. It's just separated them, right? Just like our projectile motion problem. So at t equals negative pi-4, x equals cosecant squared of negative pi-4, which is just some number. We'll come up with it. And y equals cotangent of negative pi-4, right? Probably helps to maybe just throw down a quick unit circle. So if there's our unit circle, where is, yes ma'am,
You need minus one on the x.
what'd I forget?
Squared. Negative out.
Oh, -1, yeah, there is a -1, there's, like that? Is that good? Okay. Okay, so on the unit circle, where is the angle -pi/4?
It's at, it's down there in quadrant 4.
Quadrant 4,
Degrees in
good.
quadrant 4.
Okay, so it's right
Yeah.
there, isn't it?
Yeah.
So we're just gonna go backwards, negative direction is the, backwards direction for sweeping out angle. We're gonna go back 45 degrees or pi/4, so we're right there. So what are the coordinates on the unit circle then at the halfway point in quadrant 4? Good, okay, so they're gonna be the same, just opposite signs. Positive, the x component's positive, the y component's negative,
That's solid.
right? Okay. So then what is cosecant of -pi/4? Now cosecant is the reciprocal of what trig function? Sine. Okay, so if we found sine, we can just flip it, right? So what's the sine then gonna be? Okay, so y coordinate, good. So y coordinate here, so we get -√2/2, right? But we're gonna flip that, right? So this becomes, this part right here is just gonna become the quantity negative √2/2 flipped is just 2/√2 squared, right? Everybody with me?
Yep.
Okay. -1,
That makes it easier.
right?
Is there any way we could do this without using
Well, there is, but the unit circle makes it so very much easier that we definitely wanna use the unit circle. Okay, that's something that's worth doing. If you need a copy of it, I think I even got one on the Moodle site. But if you don't have the unit circle pretty well memorized, spend an evening, make some flashcards, because that's gonna pay huge dividends for you. Okay, so how about this? If I square this, negative becomes positive, right?
Yes.
2 squared is?
4.
Square root of 2 squared is?
2.
So 4/2 is 2, minus 1,
1.
1. Okay, so
Wow.
so we get x equals 1. What about y? Okay, cotangent. Well, cotangent is just the reciprocal of tangent. Tangent in this case is going to be y component over x component, right? So -1,
Negative 1.
reciprocal of -1 is
-1.
-1. Squared
Oh,
is
you were close. 1.
1.
Wait,
Wait, you did.
what happened?
Okay, what's that? Oh, it's not squared. You're right, it's not squared.
There we go.
-1.
You didn't even know what was going on in the first place, did you? You didn't know anything.
Oh wait, it's just 1/1. Okay, fine, I got it.
Okay,
Come on, I got
make
it.
sense?
Makes sense.
Questions so far? Okay, so we got a point, right? You gonna survive, Andy? You okay? You gonna survive? Okay. All
What's going
right,
on?
I'll just keep going.
here we go.
She's
Don't need to. Okay, so we got a point. That's important. We know we've got the point 1, -1. Now we need a slope, right? So how are we gonna get a slope here? Well, that's just dy dx, right? How am I gonna get dy dx out of this stuff? This is a little tricky. See if anybody can come up with this. I don't think we've really looked at one like this yet.
Is that what he said?
X
Do you want to repeat?
with respect to t.
Cosecant, cotangent, all.
These were big stuff.
You were very observant, you know.
Okay, so we have x as a function of t, and we have y as a function of t. Now one option, and I don't think a very good option, would be to solve for t in terms of like y up here, for example, and then substitute that back into this equation in terms of y. So we get x as a function of y, or y as a function of x, take your pick. That's a lot of work, right? That's gonna be a lot of work. We got trig functions here. Solving for t as a function of y or t as a function of x doesn't look like a lot of fun.
No.
So is there a better option? Well, yeah, there is. There is. Remember, all I'm trying to come up with here is, whoops. All I'm trying to come up with is dy dx. If I can just come up with a product of rates that equals dy dx, perhaps those individual rates would be easier to calculate. Now, I have y in terms of t, so for one thing, we could take dy dt, but what would I have to multiply the rate dy dt by to end up with the overall result, dy dx? Okay, dt dx. And there's two ways to think about this. Did everybody see that? That's our ratio form of the chain rule, isn't it? Right? Because we know that the middleman here is the rate t. Algebraically, the dt's cancel, right? Another way to think about this, which is equally good, and in fact, maybe even easier in a way, is this one. What if we said dy dx equals dy dt divided by dx dt? Same thing, isn't it? Right? Does that make sense? Okay. Doesn't matter which way you do it. I mean, it's really just going to be a matter of, now we go back up and we look at our original equation, and let's just evaluate let's differentiate both of those with respect to t. So if we have x equals cosine squared t minus 1, cosecant, wasn't it? Not cosine. Yeah, cosine.
It's not
Is that a T?
Yes.
That's a t. Sorry, got t. Okay, and
Just ask.
okay.
Wait, is it negative?
Positive.
Whoa, yeah, why is it negative?
Is it not negative? Do I keep writing this down?
No.
Oh, you're right. It's positive.
What happened? What is that, my gosh? T.
Well, we're going on.
Oh, wait, going on.
Okay, so what about this top one? What's dx dt?
So,
How am I gonna probably rewrite this? Okay, I could probably rewrite this as that squared. Remember, that's actually the outer layer of that composition, right? We got a multi-layer function, and that's really cosecant t quantity squared minus 1. Good. So then, by the chain rule, 2 cosecant t time, and then derivative of negative 1, of course, is just going to be 0, right? Okay. Okay, times the derivative of cosecant t is what?
What was that? What? Cotangent squared? No.
Negative cosecant t
cotangent.
tangent t.
So wrong.
No, it's not.
Okay, good.
I tried.
So there's dx dt, right?
No, you were not.
What about dy dt? What's the derivative of cotangent t? Okay, good. And so remember that we're just trying to calculate the value of the derivative. We want the slope when t is negative pi fourths, right? So we can just evaluate both of those two rates at pi fourths, at negative pi fourths.
dy dt.
Okay. Negative cosecant squared t. Okay. So Yeah, so we'll just evaluate these. I think we've already done a lot of stuff. Cosecant we said was 2 over the square root of 2, right? Because we flipped square, right? Does that make sense? Cotangent we said was -1, right? And so this gives us,
Wait, what about the other one?
hang on, it was negative. No, yeah, it was, cosecant was,
Positive.
So it's just
cosecant would be, secant is gonna be reciprocal of, cosecant reciprocal of sine. And so it was okay, so that was negative, right? So this was -2 over square root of 2. I better write this all down.
Yes, please.
So we get negative, whoops, right?
Which is not equal to square root of 2.
That's this guy, times -1. So I've got a total of 3 negatives there.
It's gonna be negative.
So the product's negative. And I'm just gonna get 2 over the square root of 2, which is really just square root of 2, isn't it?
Yeah.
So I end up with
Wait, what?
this,
I know. I said that a long time ago.
right?
Oh, okay, yeah, I get it, never mind.
Okay? Now, what about cotangent? So cosecant, we said was negative,
Wait,
Square-
Yeah, what happened to the
First
first
cosecant.
cosecant t?
Times 2.
oh, you're right.
Okay, I was like, oh gosh, that's not it.
You're
is
right.
it?
Yeah, I was just looking at this. You're right,
Right.
you're right, you're right.
It's okay.
So we're not done.
No.
2 times cosecant was negative square root of 2,
Yeah.
Yeah, negative 2 over the square root of 2.
times all this stuff we
Yeah,
said
yeah,
was
yeah.
just negative square root of 2.
Yes.
So that gives us positive
Thank you.
2 times 2.
4.
Makes sense.
Okay. So dx dt at that particular time is 4, right? Okay, what about dy dt? This one's a little easier,
Yeah.
thankfully. So we get negative, and then we said this was 2 over the square root of 2 is just square root of 2. Squared.
Is it a negative?
Is that right?
Yeah.
Yep.
So it's negative 2.
Okay. So we get negative 2.
Sweet.
Okay, so now we can go back up here, and we can use either one of these. Now, do you see why, in a way, this one's actually a little bit easier?
Yeah.
So this gives us dy dt was negative 2, divided by dx dt was positive 4. Yeah, okay. So dy dx at our time is negative 1/2. That's the slope of the tangent line. We've got our point right there, right? And I mean, do we even want to finish it then? We know we got a point, we got a slope. All we have to do now is just plug it in, right? Does that make sense? Yeah, good. So we'd end up with, and what I favor, I mean, you can use point slope if you want to, but really, once we know these two things, it's pretty easy for us to just say, let's just start with y equals mx plus b. I just have to figure out what are m and b, right? We know m is negative 1/2, so if I plug negative 1/2 in for n, I plug 1 in for x, negative 1 in for y, I can solve for b, right? That make sense? Okay, and we're done, okay? So that's a lot of work, but let's just kind of reflect on that for just a second and see what we found here. This is not that bad a problem. You know, I mean, whenever time you're taking derivatives of trig functions, it's an extra wrinkle in the problem, but being as we know that we're going to evaluate our derivatives when t equals negative pi over 4, it's not that bad, right? We just differentiate dx dt and dy dt, and we use the chain rule. Probably the trickiest part is right here, is remembering that,
Yeah, that's tricky.
you know, we're using the chain rule to construct our derivative, dy dx.
Yeah.
From dy dt and dx dt. Okay? Does that make sense? Questions on that? Okay, there's a couple of them on there. I'll tell you, on the practice test, you'll see this. There is gonna be a problem on the test that where you're asked to do something like this, just because I think that using these parametric equations is such a big deal. Maybe not this year in our class as much as, you know, in physics and in future years, but just being familiar with how to deal with parametric systems like this is really useful in math, science. Okay. Okay, this one I'm confident we can just skip this, because really this is just like a related rates problem that's done for you.
Oh, yeah.
Right, if they're telling us, if they want us to find the SDT when theta equals pi, if S equals cosine theta, this is really just a matter of differentiating implicitly with respect to t, isn't it?
Yes.
Right? So we get, if we know that, here's our parent equation. Whoops. So here's our parent equation. S equals cosine theta. All I'm doing is just implicitly differentiating with respect to t and then plugging in values, right?
Mhm.
Does that make sense? If I'm trying to find the SDT, well, I just get S dot equals, what's the derivative of cosine theta with respect to t?
Is dot the same thing as?
What's the derivative, now what's the outer layer here? Good, okay, yeah, we got a cosine of hand, right? So negative sine hand times derivative of hand with respect to t,
And
Should be d theta over
Yeah.
dt.
theta dot, yeah.
theta dot, right?
And dot.
So same thing.
Okay.
Am I right?
We already.
Yeah, oh yeah, dot is, you might have been gone for that. Dot means differentiating with respect to t. Yeah.
And we already
T
have that,
replaced.
so.
Exactly,
Yeah.
look, here's theta dot,
Respect to t.
right? We know theta is pi, so that makes that easy. And so all we do then is just
Yeah.
plug and chug, and we're there.
Plug and
Two
chug.
pi.
That can
Well, what's the sine of pi?
So that might have seemed like a difficult problem at the time, but
That is
now,
suggestive.
no big deal.
I feel a little uncomfortable.
Sine pi zero.
Sine at pi is
Times two is obviously
0, yeah, yep, yep, good.
It's
Yep.
obviously two.
Right.
Okay, little kinematics here,
Oh, I don't like kinematics.
Oh, what?
Right?
okay? So they're giving us a position function, right? Here's our position function. Now, you gotta write it, it's probably better to write it this way,
This is easy.
right? Write it in terms of the parameter t, because it's a function of time, right? So S of t equals that. Square root of 52 plus 4t. And then all we're doing, really, this is just a disguised differentiation problem, right? If we're differentiating, what is velocity in terms of position?
Derivative of
Well, yeah, okay, velocity, remember, velocity is just the derivative of position, right? It's just ds
Yeah.
dt, so it's just s dot.
Huh.
Right?
What's that line?
Oh,
It's
that's my
extent.
vector, ignore
Yeah.
that. It's just
Yeah.
because these are vector, we don't even need them, just vector,
Yeah.
they're vector quantities in physics, but
Are you gonna take
gosh.
that's probably, let me get rid of those.
You know what they are.
Yeah, they use those.
Those are scary, we'll get rid of those.
Yeah, I was like, I'm a junior.
You don't need to know this.
They're not scary, they don't.
Dude, I'm learning about moles here and.
Yeah.
Molar mass.
Okay, what's acceleration?
That's fun.
I forgot about that.
What's acceleration?
Is it s dot dot?
Yes, it's the derivative of velocity with respect to time,
Wow.
so it's v dot
Lady.
s double
I'm a
dot.
clutch.
That's all it is. Okay, so very simple.
What perfect.
The reason I even assigned that is I just want you to make that connection. Really, this is where kinematics is calculus. Okay. And then if we wanted to evaluate these when t equals 3, well, that's okay. I mean, we're gonna get answers in terms of t.
Mhm.
Plug in 3, right? Here's a question, can I plug in the 3 before I differentiate?
No. No.
One more time, everybody get that question? It's an important one. Can I plug in the 3 before I differentiate?
No.
No, never. You can't plug in the values, you can't evaluate
Never.
until
Never.
after you do the calculus, right? If I plugged in the 3 initially, these would just look like numbers and their derivatives would be 0. That's
I
obviously
like
not right.
numbers.
I dig the numbers.
I dig numbers. See variables? I like.
Okay, moving on. This guy, let me make this bigger.
That is
Do
chill.
it.
Oh, I know how to do that.
You can do this, guys.
You sure?
Mhm.
Sure, like,
Challenge yourself.
Challenge.
Yeah, I'm pretty sure.
Accept the mundo.
they're taking the derivative.
Oh, I can do that.
Okay, so if we're trying to find dy dx or y prime.
We have to use probably.
Okay, good. So this is a mixed up problem here, where we don't have, this is implicit as opposed to explicit. We don't have y as an explicit function of x, and it's really hard to get it that way. So we're not even gonna try. We're just gonna implicitly differentiate with respect to x using chain rule. And then when all the dust settles, we'll just solve for y prime, right? Now what's nice about this, and you've done enough of these already that you've seen this pattern, but you know that, for example, if I just look at what the outcome is gonna be in general for each of these two terms, let's just take the first term. I know that I'm gonna get some combination of kind of, you know, inconvenient rules and lots of algebra stuff, but when I use the chain rule, whatever I get with my first layer, the second layer is just gonna be a y prime to the first power, isn't it?
Mhm.
So that's what's nice. I always know that I'm just gonna get y primes out to the first power, and so they're always gonna be easy to isolate on one side, right? So let's maybe, you know, I mean, you guys have done a lot of these, but let's just go through, you know, just kind of collect our thoughts and go through one of these. Are we about done? How much time we got?
It is done.
This is it.
Oh.
That was a
Bell's supposed to ring
but-
right now.
That's right, today is short day, yeah.
I don't have.
Okay, we'll just pick it up. We got a few more to finish up, related rates problems tomorrow, and then test Wednesday.